Oh, no, we don't want that.
All right. Well, thanks very much for the invitation to speak this evening. And what I have for you as advertised is a talk about overloading in C++. How does it really work? So, well, oh no, this is the wrong kind of overloading. Yes, not that either. No, not quite. No. No, not that movie. No. Okay, we're getting closer. It's really amazing how often the word overload has itself been overloaded. But with that behind us, here's what I've got planned for us this evening. I want to talk just a little bit about the origins of overloading, and then a few words that illuminate some of the principles that underlie overloading. We'll talk about algorithm for selecting among overloaded functions. Then I'll spend a fair amount of time looking at a number of scenarios and subtleties of overloading. And as we get to the end, I'll have an advanced case study or two with which we'll conclude the talk. So let's get underway. And I just stopped. I'm sorry, let me get back to PowerPoint. There we go. Okay, so a little bit about the origins of overloading. Let's just start by thinking about the expression x plus y. What does the plus operator mean in that context? Well, without more information, it's really unclear how to go about obtaining the intended result. Now, if this were mathematics, we'd evaluate the expression based on the kinds of entities we are denoting by x and by y. For example, if they were both whole numbers, we do it one way. If they were fractions, we'd do something else. If they were matrices, we'd follow a different algorithm. The point is that the same notation can imply different techniques, and that the method that's going to be used depends only on the operands. So operators are, well, let's quote from D&E. Operators are used to provide notational convenience. When variables can be of different types, we must decide whether to allow mixed mode arithmetic or to require explicit conversion to a common type instead. By choosing the former, as other languages have done, C++ entered a difficult area without perfect solutions. This results in a fundamentally difficult problem, namely, the desire for flexibility and freedom of expression clashes with wishes for safety, predictability, and simplicity. This was written almost 30 years ago. So, as we know, the net outcome is that C++ supports operator overloading, just as many other programming languages do. Even Fortran back in 1957 supported operator overloading, what we used to call mixed mode arithmetic. But C++ supports also the more general feature that we term function overloading. So by treating operators just as functions with funny names, as in operator plus, for example, we obtain a coherent set of rules for all overloading, whether we spell a function plus and call it with prefix notation, plus of x and y, or whether we spell it operator plus and call it with infix notation as x plus y. So for today, I'm going to focus mostly on named functions but essentially everything I will talk about will apply to operators as well. So what are some of these underlying principles? Well, what C++ has are overloaded declarations. And a C++ name is described as overloaded if it meets three conditions. First, the name is declared at least twice in a single scope. Second, each such declaration introduces a function or a primary, namely unspecialized function template. And third, the declarations are mutually distinguishable. So what do we mean by that? Well, let's kind of back into that for a moment. Let's look at some examples of what kinds of declarations are indistinguishable. A redeclaration, of course, is not distinguishable from the initial declaration. Function declarations are not distinguishable if they only differ in their return types or no except specs, or both. And member function declarations are not distinguishable if the only way they differ is by the presence or absence of static or a ref qualifier. So what's left? Well, function declarations with the same name are distinguishable when one declares a primary function template and the other declares an ordinary function, or they have different numbers of parameters, or any two corresponding parameters have distinguishable types. So we've sort of kicked the can a little bit down the road. Functions are distinguishable if corresponding parameters are distinguishable. Well, let's look at some examples of indistinguishable function parameters. If two parameters differ only by their name or by their default value, that's not sufficient to distinguish them. Those aren't part of the type. If one type is an alias for the type of the other, they're not distinguishable because alias is not a new type. Or if one type is the decayed form of the type of the other one. For example, one's an array type and the other one is a pointer type to the same elements. Or one's a function type and the other one is a pointer to that kind of function. Or one is const qualified and the other one is not. Okay? So let's look at some examples. So I'm going to show you a pair of declarations. And in each case, I'll stop talking for a few seconds, give you a chance to look at the declarations and decide for yourself whether this pair constitutes a pair of overloaded declarations. Let's start with this pair. So I hope you'll agree this is not a pair of overloaded declarations, because although we are declaring two functions with the same name, they're in different scopes. And to be overloaded, they must be in the same scope. Second example. These two do constitute an overload set. The parameter types are distinguishable. Now, you may be thinking that on some machines, char is an unsigned type, but nonetheless, it's not an alias. It's a distinguishable type. So this is, in fact, a pair of overloaded function declarations. Third example. This is not an overload set. The names of the parameters don't make a difference. It's not part of the type. and the defaults don't affect the types. So the second declaration is just a redeclaration of the first. They're not distinguishable. Here are some more. This one's kind of interesting. Yes, this is an overload set. Even though the function part of the template looks almost the same as the first declaration, the function, a function template and a function overload each other. So this works. Next example. No. The second declaration is a redeclaration of the first. A parameter of function type is indistinguishable from its decayed type, which is here pointer to function. So these two are indistinguishable. These are redeclarations, not an overload set. This one's kind of interesting. These are, in fact, overloaded. We have a parameter, a function that takes one parameter and another function that takes two parameters. So they're distinguishable. On the other hand, if you actually were to make a call with only a single argument, that's probably going to turn out to be ambiguous. But nonetheless, it's a valid overload set. Let's look at a few more. Looking now at member functions, the base class and the derived class, and each declares a member function by the same name. Is this a valid overload set? And the answer is no, simply because these declarations are in different scopes. Moreover, the declaration in the derived class hides the declaration in the base class, so never will both declarations be visible at the same time. Now, if we tweak this just a little bit, this is essentially the same example, except that I've added a using declaration. Does this, in fact, change anything? And the answer is yes, it does. This is an overload set in the definition of struct D in the derived class. The using declaration brings the calc8 from the base class into the scope of the derived class, where there is also a distinguishable calc8. So we have an overload set in the derived class. But if I were to change that declaration slightly so that the declarations were indistinguishable, then the declaration from the base class would be hidden despite the using, and only the declaration from the derived class would be visible. So there's some subtleties here. All right, let's move on a little bit, and let's consider the notion of selecting among overloaded functions. If we look at the clause in the standard, in the C++ standard, there's an entire chapter, which we refer to as a clause. It's about 33 pages last time I looked. Very densely written description, specification of what overloading means. And it begins by saying, when a function name is used in a call, which function declaration is being referenced is determined by comparing the types of the arguments at the point of use. And that's going to be compared with the types of the parameters in the declarations that are visible at that point of use. And this process of selecting the right function is what is termed overload resolution. So let's look at overload resolution from the compiler's point of view. And I really wanted to number my bullet points on this slide starting with 0, and PowerPoint just won't let me. I don't know why not, but somebody decided I can't have a bullet numbered 0. So this is number 1. Overload resolution is initiated from a named function use. If you're calling via function pointers, for example, there's no need for overload resolution. We're already pointing at the function we intend to call. It's when we have a name and there are multiple declarations for that name that we have to go through overload resolution. So what does the compiler do? Well, initially, it prepares a list of candidate function declarations. And it gets those function declarations by doing appropriate name lookup, or more than one lookup. And any kind of name lookup may add a candidate to the list. It could be unqualified lookup, qualified lookup, argument-dependent lookup, and so on. Lots of different kinds of name lookup. Any one of them can add to the list of candidate function declarations that need to be considered. Along the way, a couple of interesting things could happen. For example, name lookup might have found a function template. Well, a function template does not declare a function. It declares a template. But the compiler knows how to use that template to synthesize a function declaration from it. If that synthesized function declaration happened to be ill-formed, it would be just discarded. It would never go into the candidate list. Silently, it's not an error. This is what has been termed svine. It's not an error. It's just discarded. It doesn't go into the candidate list. This is an important point. Not that it's silently discarded, but that the template is not a candidate. A declaration that is synthesized from the template can be a candidate, but never the template itself. And another interesting possibility, if we happen to be dealing with constructors, the compiler has to consider deduction guides as well, ever since C++17, because they can produce information that is useful to decide which constructor to call. Okay, so at this point, the compiler has produced a list of candidates, but not all of them are necessarily good candidates. So the next major step is for every candidate, let's say its name is C, this compiler will determine whether C is viable. Namely, is it really a good candidate? So in particular, do we have the same number of arguments as we have parameters in the declaration? And of course, we have to account for default arguments if there are any, and we have to account for an ellipsis parameter if that's present. But after accounting for all that, do we have the correct number of arguments to match with the number of parameters in the declaration? And if the answer is no, this is not a viable candidate. Second, we need to consider whether each argument can initialize the corresponding parameter. Now, that initialization could happen directly, or some kind of conversion, a promotion or a decay, or maybe there's a reference binding involved. But is it possible for the argument to initialize the corresponding parameter? If the answer is no, then this is not a viable candidate, and it's discarded. And one more interesting consideration. If there are associated constraints ever since C++20, if those constraints are not satisfied, then this is not a viable candidate. The constraints only come into play as a tiebreaker, and we'll talk about that later. We have multiple constraints, multiple declarations, and they all have satisfied constraints. Those are going to become tiebreakers. We'll talk about that in a little bit. The next step is for the compiler to decide on which is the best of the remaining, namely viable, candidate function declarations. And that the details of that are going to get its own page. But once that has finished, overload resolution will be considered successful if and only if there is exactly one viable candidate that is a better function than all the other viable candidates, and that exactly one viable candidate is accessible in the context of the use. So if overload resolution succeeds, now for the first time, the compiler cares about the definition of the function. We haven't done anything with definitions yet. Everything has been declaration only. If overload resolution succeeds, the function definition corresponding to the chosen declaration will be applied in the context of the use, typically a call. And if that declaration had been synthesized from a function template, now it's time for that function template to be instantiated. And we get a specialization. And that's what's going to be called. Okay? Otherwise, the whole program is considered ill-formed. All right, so let's back up a little bit. What are some of the criteria that the compiler will use to decide for any two viable candidates which one is it considers better? Well, one question the compiler asks is how many conversion steps are needed to initialize a parameter with the corresponding argument. And the preference is for the candidate that needs fewer steps. A second criterion: if one of the parameters has R value type and the other one has L value type, we'll prefer the candidate that has the R value type. If we have a pair of candidates and one has a parameter of a derived class type and the other one has a corresponding parameter of the base class of that derived type, the compiler will prefer the candidate with the derived parameter type. If one of the candidates is an ordinary function and the other one was synthesized from a template, we're going to prefer the ordinary function. So that's a sample of the considerations that the compiler gives when it compares pairs of candidates that have been all considered viable. And after considering all the pairwise candidates, it's going to try and end up with a single viable candidate that it considers best. If it can't, if there are none, or if there's more than one, we have an ill-formed program. So the big picture here is, quote, the candidate function whose parameters match the arguments most closely is the one that is called. But keep in mind that overload resolution might be needed wherever a function name may appear, and that's not only in calls. So here's a short list of possibilities. Function name could appear as an initializer in a declaration of an object or a reference. It could appear on the right-hand side of an assignment. Excuse me. It could be an argument to a function or to a user-defined operator or to an explicit cast or a static cast. It could appear as the operand of a return statement. It could appear as a non-type template argument. So in all of those cases, the compiler may need to perform overload resolution. Of course, at least in my experience, the overwhelming majority of the time, the reason for overload resolution is because we have a function call. But overload resolution happens for any and all of these other reasons too. Okay, moving on. I'd like now to show you a number of scenarios involving overloading, some of which have some fairly subtle features involved. But I'll phrase a number of them in the form of questions, and then we'll go right and look at the answers. So, scenario one. What if there's a candidate function that's defined as deleted? In other words, something that looks like this. Well, that's a definition, but all definitions are also declarations. So that's a candidate if we're calling G. Well, overload resolution considers only the declarations and doesn't care about the definitions until it's found the result and succeeded. Therefore, how a function is defined is not relevant to the overload resolution algorithm. Doesn't even care whether a function is defined. It's the declaration that overload resolution looks at. Now, of course, if overload resolution ends up selecting a function with a deleted definition, that's the best viable candidate, then the program is just ill-formed. Pretty much in the same way that a function that we've declared and called, but not defined. That's an ill-formed program, right? That's often a beginner's mistake, who declares a function and never provides a definition and tries to call it anyway. You can't do that, of course. So for the same reason, you get into trouble if you try to do that after overload resolution. Okay, next scenario. What if I have a candidate that's a member function and it's been declared private? So it might look like this. Well, again, overload resolution considers only the declaration, not the accessibility. So where it's declared is not relevant to the overload resolution algorithm. But if overload resolution has succeeded and discovered that a private member function is the best viable candidate, the program ends up being ill-formed. because we have a function that can't be called. It's inaccessible. So even private members affect the interface to a class, at least in this scenario. Okay. Next. Here's a pair of types, wrapped long, wraps a long, and wrapped short, wraps a short. Nothing overloaded here, so let's now look at a pair of functions involving these types. They're both named G. One takes a parameter of type wrapped long, the other takes a parameter of type wrapped short. This is a valid overload set. The parameters are distinguishable types. Now let's look at a call. And I'll tell you up front, this call is ambiguous. Take a moment to think about it. I'll be right back. So what's the problem? Well, it's true that the parameter named, or the parameter whose type is wrapped short cannot be initialized from this argument because there's a narrowing conversion involved, right? And a million can't be represented by a 16-bit short. But overload resolution inspects only the type, not the value. So the fact that it can't be initialized does not affect the outcome. And the last time I checked, not all compilers correctly implement this rule. So you may not get the result that I'm claiming here. But you should also know that this rule is being reconsidered for C++23. So this might not be around for much longer. Nonetheless, this is C++20. Next, is this valid code? Now, I must tell you that I wish the answer were no, but it is valid code. Even though the identifier capital S is multiply declared in a single scope, this is not considered overloading. There are no functions declared here. Overloading in C++ only admits function declarations and declarations of function templates. We have neither of those here. So this is not an overloaded scenario. But this is valid C++, mostly, I believe, for historical reasons. Specifically, this feature, which I frankly consider a misfeature, is what is termed an elaborated type. And if you've not encountered this before, the rule is that the name of the variable hides the name of the type. Except that you can unhide the name of the type if you precede it with an elaborated type specifier, namely struct, class, or union. So even after that pair of declarations, if you say S, you're talking about the int. If you say struct S, you're talking about the type in the same scope. Please avoid this kind of code whenever you can. Let me show you a specific example of this. Let's declare a class S. Now I'm going to declare a variable by the same name of that type. So now I have a variable and a type by the same name. And remember, the name of the variable hides the name of the type. So if I try to declare a second variable t, that doesn't work because s is the variable. But if I bring back the elaborated type specifier and I say class s, I can now declare another variable because this s is a type. I consider this perverse. Please avoid it to the maximum extent you can. Nonetheless, it's valid C++, and I believe for compatibility reasons, it's probably never going to go away. That doesn't mean we have to use it. Okay, let's look at another scenario. It's a fact that sometimes the compiler does overload resolution twice at the same point of use. Here's an example. Here's a type that can only be copied, it cannot be moved. I've given a default constructor, and I've given it a copy constructor, so there's no implicit move. Okay. Now let's have a function, go. It returns an entity of type copy only. So I create a local variable x of that type, and I return it. Well, the language says we want to do copy elision. Move, we want to do moves in preference to copies. So what does the compiler actually do here? It first treats the x as an R value while it's doing overload resolution. If that were to succeed, we're done. But that can't succeed here. There's no move constructor. So now we're going to treat x as an L value and do overload resolution all over again. And this rule is also being reconsidered for C++23. And we should know probably in a few months whether these two rules that I've alluded to will actually be changed. But C++20, that's the rule I've quoted. Okay, next scenario. Suppose I have both a primary function template and an explicit specialization of that template. So we have two declarations by the same name. Do we have an overload set? And by now, I hope you will quickly answer no. Because neither a primary template nor any specialization is ever a candidate for overload resolution. The primary template is consulted perhaps so that a function declaration can be synthesized from it. But the primary template is itself not a candidate. The synthesized declaration would be. And specializations don't enter into this at all. Specialization is a definition. It would only come into play if overload resolution picked the synthesized declaration for which we have a specialization. Okay? Overloading considers function declarations only, A template does not declare a function. Function declarations can be synthesized from a primary template. When function templates are involved, declarations, not definitions, declarations that are synthesized from the primary template become candidates that are considered by overload resolution. Well, suppose overload resolution does select a synthesized declaration. Now what? Well, I've alluded to this, but I want to mention it one more time. At this point, we're going to need the corresponding specialization, which is the definition of the function we want to call. And if it's produced from a template, it's called a specialization. The process of producing a specialization is called instantiation. But there are two possibilities. One possibility is that the programmer has provided an explicit specialization, in which case that's the one that the compiler will use and ultimately call. Otherwise, the compiler must instantiate a specialization from the definition of the primary template. Okay. What if overload resolution comes up with a tie between candidate declarations that were each synthesized, but from different function templates? Well, ordinarily we'll say we don't have a single best candidate. But there's one more step. And some people consider this part of overload resolution, and some people say, no, it's a post-processing step, but it doesn't matter. It comes into play in exactly this situation. It's known as partial ordering. Partial ordering is used to resolve ties when you have synthesized candidates from distinct function templates. If one candidate is more specialized than the other, it's considered better than one that's less specialized. If one candidate is constrained, and here we're talking C++20, if one of the candidates is constrained and the other one is either unconstrained or less constrained, then the more constrained candidate is considered better. Okay. And by the way, the reason this is called partial ordering is because we cannot break all ties this way. We can often break ties, but not always. So it's partial ordering. When partial ordering succeeds, overload resolution is deemed to have succeeded. Otherwise, overload resolution is deemed to have failed. Okay, next scenario. Suppose we have declarations that originate, or at least some of them originate, I just called it elsewhere, meaning not here. For example, here's a declaration that originates here. Here's a declaration, extern. We haven't seen that yet today. And to stir the pot a little bit, let's throw in a using, introducing a name from yonder. So can we do this? Is this a valid set of overloaded calc9 declarations? Take a few moments, think about this. I'll be back shortly. Okay? Well, the answer is yes. If. Okay? It's conditionally yes. Each calc9 declaration from namespace yonder must be of a function or function template that is distinguishable from the first two declarations. Remember, it's only an overload set if all declarations are distinguishable. In my experience, I haven't had to do something like this very often, but there are rules that cover this scenario. We have more. When you use a default argument, you're not overloading, but you're making a choice to avoid overloading. Let's take a look. Here's one possibility. I declare a function and provide a default argument. Or an alternative, declare two functions. No default arguments, but the only thing the second one does is to call the first one. And it turns out these aren't quite the same. They have similar effect, but nonetheless, they have slightly different implications. Keep in mind that a default argument, just like every argument, is supplied at each call site, right? In other words, you can think of it as default arguments are inlined. If I call this function multiple times, I'm going to get probably multiple copies of that default argument, right? On the other hand, if I were to use an overload set instead, as shown in bullet 2 above, I will have only one copy of this value, and it probably won't be in line. It'll be local to the body of the function. Let me quote D&E again. Given general function overloading, default function arguments are logically redundant and at best a minor notational convenience. Remember, this was written almost 30 years ago. However, C with classes had default argument lists for years before general overloading became available in C++. So if you're thinking about using default arguments, please think about using overloading as an alternative and make an informed choice. By the way, there's one more reason you might want to prefer overloading. Take a quick look at this declaration. yes, there's a default for the function argument. But when type inference is involved, default function arguments don't play any role. So if you try to call G with no argument, that won't work. It's not the same as calling G of 0. If you really want that to work, you're going to have to provide a default for the template argument as well. Right? Type inference will still fail, but the more general type deduction will say, oh, I can't infer the right type, but hey, there's a default there, so that'll be the type I use. And now the 0 comes into play, but only after we know what T is. And by the way, default arguments interact with virtual functions. Let's start with a base class with a member G, a virtual member G with a default argument. Now let's have a derived class that overrides G and provides a different default. Okay. So what happens when we call G? So let's have a variable little d of type big D. We'll call d.g. This is not a virtual call. There's no dynamic dispatch. We don't involve the V table. We call the G defined in the derived class. It has a default of 43. Now, let's initialize a variable B as a reference to the base, but we'll initialize it with D. We'll call b.g. Well, now we're doing a dynamic dispatch because we have a reference involved. And when you go through the base class, you get the default from the base class. So this is going to display. We're still going to call the function in the derived class because the dynamic type is of the derived class. But we're going to end up taking the default from the base class. So this is probably a scenario we would do well to avoid. Here's another scenario that came up, just a few months ago. Somebody posted this as a question. It says, which function G is going to be called? So first, let me show you the functions. All right. Is this an overload set? Well, yes, the types are certainly distinguishable. And now let's look at a pair of calls. Please take a moment to think. Let me give you a hint. Consider the type of the arguments in the two calls. Okay. Well, I hope you found it, number one, to be fairly straightforward. It's pretty clear that the argument K in call labeled 1 has type int, and an int can equally well initialize parameter P1 and parameter P2. So this call is ambiguous. And I hope you find that fairly straightforward. Call number 2 is a little more interesting. The type of the argument is also int. And I know an awful lot of programmers would tell me that this has type int ref because that's the return type from standard move. It does not. It's a PR value expression, but its type is int. And since the type is int, call at number 2 is just as ambiguous as the call at number 1. What's the rule that governs this? There are no C++ expressions that have a reference type. Never. There are no C++ expressions of reference type. There's a rule that says if an expression seems to have a reference type, that reference type is very quickly stripped off, and now we no longer have a reference type. So the type of an expression is never a reference type. The reference type can affect the value category of the expression, but it still does not have a reference type. So I hope you found that one interesting as well. Here's a scenario that I've excerpted from the standard itself. Let's start with a pair of types A and B. And other than their name, they are almost identical, except I've reversed the order of the members. There's an XY, and the other one is a YX. Now let's have a pair of functions. They're overloaded. They're clearly distinguishable. They're different types. One takes an A, one takes a B. And now let's look at a really interesting call. And this is, as the comment says, involves aggregate initialization, because A and B are both aggregates, right? There are no constructors in sight. These are very simple types. They're aggregates. So aggregate initialization applies. And further, we're doing aggregate initialization. Instead of just saying 1, 2, we're using a what's called a designated initializer list. So this is valid C++ 20. So which one is being called? The G that takes an A or the G that takes a B? And I believe no matter what your answer is here, you may find the reason somewhat surprising. First of all, the answer is that the call is ambiguous, which I know several programmers have told me they find surprising. Nonetheless, this is ambiguous. And the rule which I'm quoting here is that aggregate initialization does not require that the members be declared in designation order. Okay, but that's not the whole story. If after overload resolution, so we can do overload resolution just as is. If after overload resolution, if the order does not match for the selected overload, assuming there is exactly one, if the order does not match for the result of overload resolution, the initialization of the parameter will be ill-formed. And I should also point out that the last time I checked, not all compilers correctly implement this rule yet either. Now, that may have changed since the last time I checked. I hope so, but I'm not sure. So let me show you just one more scenario here. This is adapted from a recent bug report. So first I actually define a function template. And then a function, use1, that calls a specialization of that template. Now, it should be pretty clear that it's foo of int that's going to be called, right? And that that's going to be instantiated from the primary template that I've labeled number 1. Now, let's keep going. In the same translation unit, I declare another function template, which I've labeled number 2. And the only difference is I've put in a requires clause. Fairly trivial one, but nonetheless, it's a requires clause. And now a second function, use2, and it makes an identical call as we saw before. So now I have 2 function templates, each of which can synthesize a function declaration, and those look identical. So which one is going to be called from inside use2? Well, overload resolution is going to select the foo event that comes from template number 2 because it has a constraint and the other one doesn't. And we prefer constrained functions when they're satisfied. And of course, true is always satisfied. It's never false. Well, so much for overload resolution. But we have a big problem. A rule that says you can't change the result of overload resolution for a given call. So we're doing a given call from 2 different places. They are required to have the same result from overload resolution. Since they don't, we end up with an ill-formed program with no diagnostic required. I found this interesting. I hope you did too. In this part of the standard, we have the following specification. If multiple declarations were found in different scopes and specify a default argument that made the function viable, the program is ill-formed. Huh. How can that happen? Well, let's start like this. So here I have 2 distinct namespaces. Each declares a function g with the same default argument. They're both declared with extern C linkage. Now we'll use a using declaration to bring both of them into our scope. Now we have an overload set. Now let's try to use them. Okay. The extern C is important to this example. Okay. There's declared extern C, there can be only one such function. No matter how many times I declare it, there's only one such function, and it's defined somewhere else. Okay. So if I call it by saying g of 3, that's okay. I didn't use a default argument. But if I call it without an explicit argument, that's an error because of the rule that I cited at the top. Okay. Well, I hope you've enjoyed looking at these scenarios that explore a number of subtleties and rules of overloading and overload resolution. I'd like to leave you with the last few minutes by showing you what I've dubbed an advanced case study involving overloading. As we've learned, and as many of you already knew, I'm sure, overloading involves functions. But we also have other entities in C++ that are callable. Can we overload callables that aren't functions? In other words, if I have a number of function objects, and each of them has a type that has this form, namely, they all have a call operator. Okay? And that encompasses an awful lot of function objects. As I mentioned in the footnote, every lambda that has a closure type of this form, all function objects of class type have this form. And a particular example of that in the standard library is function. All right? Any class type that has a call operator as a member has this form. So the question is, can we provide them under some common name? Now we know we can't name all the structs the same. We're not allowed to overload type names. But can we nonetheless provide them under some common name so that overload resolution would apply to their call? So what I'd like to do looks something like this. I'd like to declare an object named, let's say, Go, of some overload type, which I instantiate by providing my function object instances. Not the types, the actual instances of the function objects. And then once I've done that, I want to be able to say go and supply appropriate arguments and have the compiler do overload resolution on all of the operator parens, all of the call operators in all of these function objects, and call the best one. And yes, we can do that. And it turns out to be astonishingly simple with the right tools. We use parameter packs, inheritance, and a using declaration. So the plan, we're going to inherit from each of the function objects, and then we'll bring each of the call operators into our scope. And the whole thing looks like that. That's it. That's complete. We declare a template, and the template parameters are the types of our function objects. We'll treat them as a pack. And we're going to inherit from those. Right? And then we're going to bring all of their operator parens into our scope. And we're done. And how would we use this? Like this. Supply overload, in this example with a pair of lambda expressions, each of which, of course, produces a closure. We're relying on aggregate initialization. I mean, there are a couple of caveats. We have to be sure that none of these function object types are marked final, because then we couldn't inherit from them. That's relatively uncommon in my experience. So there are just a couple of restrictions, but nonetheless, this is all it takes. And finally, can we do something similar, but control the order in which candidates are considered? And it turns out we can. And it turns out this is incredibly useful, because especially in recent C++ standards, we're getting more and more specifications of the form, if this condition holds, then you call the function this way. If this other condition holds, and it's an otherwise, right? So if the first condition doesn't hold, but the second condition does, then we'll call it this second way. Otherwise, if this third condition holds, we'll call it this third way, and so on. And although this can be coded in other ways beyond what I'm going to show you today, it's incredibly tedious by the time you factor in different possible return types, different possible no except specifications, and so forth. There are a number of subtleties to be considered. But let me show you something different. Given the same kinds of function objects I described before, can we provide them under some common name so that of the function objects that we provide, we call the first one that we provided that turns out to be viable? In other words, we don't throw them all into one big pot and look for the one that's best. We look at them in order. Is the first one viable? Can we call it? Yes, let's call it. We're done. No? Okay, let's look at the second one. Is it viable? Can we call it? Yes, let's call it. We're done, and so on. So we'll do that by designing a class template, which I've named first viable. It turns out there's something like this in the Boost library, where I believe it's known as first of, but its implementation is quite different from what I'm about to show you. So what I'm going to say to you is that we're going to distinguish the first parameter, which I've named little f of type capital F, from the rest of the parameters, which will be a pack little fs of type capital Fs. And this is rather Lisp-like, isn't it? But this is fairly common when you deal with parameter packs. I'm going to treat it as if it had a head and a tail. A head consisting of one object and a tail consisting of all the rest. And the point is, if the head is viable when I supply it with appropriate arguments, we'll call it. If it's not viable, I'm going to call the first one that's viable from the rest. And that's the entirety of the plan. Okay? So let me show you a little bit of code. We're going to start with an empty primary template, because there might be cases when nothing is viable. So there's nothing to call. Then we'll provide a specialization that'll do all the hard part. It's going to check all the viability in order. It's going to span 2 pages. Here's the start. All right, the template parameters are the head and the tail. They go into the specialization. And I'm going to have 2 members named first and rest, the head of the list and the tail of the list. So I'm either going to call first or I'm going to call rest. Okay, and here are the details. We need a constructor. It'll look like that. And then for the meat, instead of reproducing all that several times, I'm just going to abbreviate it and label it case 1. And I'm going to have a case 2 that looks like that. Notice they're almost the same. That's the only place they differ. I either call first or I call rest. In either case, I forward the same arguments. And case 1 looks like that. You see why I abbreviated by saying case 1. I had to repeat it 4 times. And notice the highlighted requires clause. This is satisfied only if and only if the call would be viable with the given arguments. So what's case 2? Well, case 2 is almost exactly the same, changing almost all the case 1s into case 2s, except the requires clause is the negation of requiring case 1. So if case 1 is not viable, we're going to handle case 2. And that's it. There's really not very much to it. There are a couple of last touches. We might want to have a deduction guide. It is possible to recode this, so instead of a pair of operator parent overloads, you could do something like this with a single one. But if you do that, notice that the return type and the no except specifications become messier. You can solve that with some type traits, but they're still going to be messier. And the final little touch is to consider, instead of using a bare call, going through standard invoke, because that understands how to call members, both member functions and member data, could also call reference values, reference wrappers, as well as function objects. And with that, I thank everyone very much. I appreciate it. Thanks for coming. I hope you found some of these remarks to be of use. And now, back to our host.
Okay, thanks, folks. At this point, we'll stop the recording and we will have the Q&A session.